Okay, this is the global script syntax overview, part 1. For this video, I'm going to be going over the source code to the global script parser for the new global script implementation that I'm working on. So all of this syntax that I'm going to be showing is implemented and does work, but it doesn't quite process itself, as you'll see. I'm going to be using Emacs, which is not my preferred text editor, but I tried recording this video using Acme and I wasn't quite satisfied that the text was going to be large enough for you to read. So we'll try it with Emacs, and we will hope that all of the Unicode works correctly. So this actual file is just a Haskell file with global script embedded into it, and then there's a preprocessor that parses the global script and compiles it down to Haskell. I could probably have implemented this as a real Haskell quasi-quote, but that would have involved learning more about Haskell than I really want to learn. So there's a preprocessor. There's a few limitations to this implementation. Most importantly, there's no type checker. So for in the real global script is a qualified function, it has a constrained type. No type checker means no constrained types. So you have to have a separate function for each type. This is the parser for function. On the other hand, as you can see, we can actually have a parser for function, and it takes generators, period, separates the generators from the body, and then the body. And so that's a fundamental concept that's going to come up a lot in global script. That's going to be a fundamental part of how global script works, is if you need to, like, you can go a really long way just with Haskell style DSLs, just expressions, but if you need to, you can go further than that in global script without necessarily having to reach for macros every time or having to reach for syntax extensions every time. Parser for essentially isn't extending the syntax, it's all declarative. So you can see there's lots of Unicode in global script. This is all literal global script source code. We have Unicode lambda, we have Unicode left arrow. We use Unicode when it's the best syntax for what we're trying to express. In global script, we put a single quote in front of every variable that we're freshly defining. So there's a single quote here, single quote here, single quote here, and then when you use the variable, we omit the single quote. So this solves the problem that you have in ML or Haskell of, in a pattern, being able to tell the difference between a pattern variable and a constructor. If there's a single quote, we know it's a variable. If there's no single quote, then we know it must be a constructor or something that we should have already seen. Lambda and for are what are called lambda-like functions or lambda-like keywords. They always have the same syntax. You have the keyword, a head, which could be different kinds of things, but of course it's always there, and then a period separating that from the body. We can tell this period from the period in qualified identifiers by the fact that a qualified identifier like this is not allowed to have whitespace in it. So the fact that there's whitespace after this period tells us it must be a separate token, must be separating the head of the lambda from the body. So, a little bit too far. This is a unary operator. It allows you can put an or in front of every alternative. You have a sequence of actions like this. You can put the then operator in front of the first one, and it just makes sequences of operators a lot easier to edit. I can delete a single line. I can delete an alternative. And things pretty much just work. I don't have to think about, am I deleting the first item or the last item or one in the middle. It's simpler. Oh, one other thing I wanted to point out here, get pose has a dash to separate words, so which is a nice feature. You might look at that and say, ooh, that's ambiguous, but it's disambiguated by the maximal munch feature of the maximal munch rule of the lexical parser, and it's disambiguated by the fact that nowadays, with screen sizes as large as they are, people pretty much put white space around most of their operators anyway. The other thing I wanted to point out, this is our string literal syntax. This is our only string literal syntax. This specific syntax is obviously copied from Perl 5. And what it does is it lets us have multiple kinds of strings without having to come up with a separate set of delimiters for each of them, which is a lot more convenient. So QQ is machine readable text. It's plain text, but it's text that you've got programmatic logic matched to. Log here is human readable text that isn't necessarily intended to be something you can put programmatic logic on. Basically, you need some level of AI or human intelligence to understand this string, whereas this is intended to be used for stuff that's parsable. Obviously, there's no way for the global script type checker to make that distinction, but types not only have a purpose of letting the machine check your work, but they also have a declarative purpose of telling the programmer what to expect. And I think it's useful to be able to say, this is text that's going to a person versus this is text that's going to another computer program. And then R is for a single character, which is a different type than QQ. And then also, this is obviously a nonce library function, parser.unit, but when we get type classes, the unit method of applicative or monad is going to be called unit. We're not going to call it return or pure. Those are just stupid names. Here we have a for with a single generator, hsgs requires a semicolon. And you can see here the new parser does as well. Eventually, we will remove that requirement when there's only one generator. So if there's one generator, you can omit the semicolon. If there's more than one generator, you have to put the semicolon after every item, after every generator. Again, because it makes it a lot easier to add and remove generators. You can just treat the generator and the semicolon as a single thing. I do think of GlobalScript as a research language, but it's a software engineering research language. It's a research language in practical terms, how can we make programming work practically? Which I'm just not familiar with a lot of languages that are really experimenting to see how can we do programming better in practice. So I think there's a niche there that GlobalScript can really occupy. Oh, by the way, if it's not entirely clear, this is the alternative function for parsers. This is sequencing. So parser 4 parses this, then this, then this, then this. Parser unit matches the empty string and just returns a particular parse tree. So parser 4 returns whatever parse tree this returns. Then matches a bunch of things in sequence and returns the parse tree of the last thing, but it discards all the previous parse trees, which is why it's useful. So here, and this particular parser is actually written wrong, so I need to refactor it. But this is the field extraction syntax. This is actually field extraction syntax for tuples. So a tuple is just a field is a record whose fields are named 0, 1, 2, etc. Eventually we'll have a special syntax sugar for tuples. But for right now, you declare a tuple. This is a record literal. You have single quote, field name. This proportional to character is the pattern matching character in GlobalScript. Then you have a field value, single quote, field name, proportional to, and then the second field value. This record literal happens to denote a tuple, but it's not a tuple literal. Tuple literal syntax will be a little bit different. But the field extraction syntax will be exactly the same for records and fields, or for records and tuples, I mean. So you can't use a decimal number as a variable. Obviously, it'll be treated as a number. But when we see a single quote, we know that's a record field name next. When we see a hash, similarly, we know it's a record field name next, and so numbers are allowed there. They have to be number literals, both because these are not decimal numbers, they're field names, and because if you put a name there, it would be a field name. One small advantage we get here over Haskell, I think, is like hash 0, hash 1, etc. work for tuples of arbitrary sizes. So tuples are subtypable, they are extensible, whereas Haskell tuples tend to be very rigid and very inflexible. This is a case analysis construct. So again, analyzes another lambda-like keyword, lambda-like function. And again, lambda and for and analyze and case are just library functions. They're library functions with attributes that tell the parser to parse calls to them a little bit differently. But they're basically just library functions. Eventually you'll be able to define your own library functions that have the same syntax. So you have analyze in a list of cases. So analyze is a function that takes a scrutiny as the first argument and a list of cases as the second argument. This is an expression. So case is a function that takes a pattern as the first argument, an expression as the second argument, and then a list of cases as the third argument. And it basically constants itself, effectively it constants itself onto the front of that list of cases. The implementation is a little bit more clever than that. So obviously, again, just like lambda, case can take a pattern as the first argument. This is a pattern that can fail. If you use a pattern that can fail in the head of a lambda, you'll get a static error. You'll get an error in HSGS. I don't know if it'll be nice, but the new global script parser explicitly gives you a nicer error that says, or tries to, that says this pattern can fail. It's not allowed in the head of a lambda. But if you put it in case, obviously that's fine because there's an alternative. So you can see this case has just been applied to two arguments. This is not a partial application. Because case is lambda-like, as a special case, we require you to supply all of the arguments, all three arguments. And if you omit the third argument, you get undefined. But for case, or for analyze, if you omitted the second argument to analyze, you get a special undefined that looks at the scrutiny, evaluates it to head normal form. So if the scrutiny is not in head normal form, doesn't have a head normal form, then you get an error or an infinite loop or whatever behavior the scrutiny has. If it does, it evaluates it to head normal form and then prints out an error message that shows the scrutiny and says, I couldn't match this. So if we didn't if S was nil and we didn't have this nil case, then you would get an error message saying, hey, I got a const, I couldn't match it. Or here, since we're doing matching on S and the first argument to S, by the time you fall off the end, you reach here, the first element of S will already be evaluated. So because we're printing out the scrutiny as far as it's already evaluated, you'll actually get to see which constructor this first element is, and then const, and then underscore, because we don't know anything about the tail. And so it's a fairly simple trick that gives you, it guarantees to give you enough information to know why did none of my patterns succeed, and what pattern do I need to add next. Excuse me. It pretty much guarantees to tell you what pattern do I need to add next to be able to make things work. So one of the limitations of it is you can see most of these constructor names are qualified. That's a normal part of how global script works. Constructor names are normally expected to be qualified, but the way the missing case logic works right now, it depends on the fact that we keep constructor names at runtime, so it'll show this as just pattern. So you have to mentally translate that to order of being dot pattern. Eventually I'll fix that. So the other thing this is the logic that figures out that the head of a lambda is supposed to be a pattern. Let's see. This is not the world's cleanest code. So the other thing in this file that I wanted to point out, again, there's no type checker, so you get explicit applications like this sometimes. The other thing is this double ampersand is short-circuiting AND. The final, we'll use the logical AND operator here in the final syntax, and it'll be parallel AND. In this case, it doesn't matter, because in practice, both sides are going to terminate. But it's something we're going to fix. But the list.memberOf operator is probably going to short circuit. So this is a conversion function. Unfortunately, GSFAR funcdatum does return. dstring is a function from string to string. It's a difference list. So this takes a difference list and turns it into a regular log value. This is expression interpolation syntax. So you say section symbol and then an expression in parentheses. At the moment, that's the only interpolation syntax that is supported. Eventually this funcdatum function, pretty much any formatting, if you're formatting for display to the user, that should all go through this log type. But funcdatum is implemented in Haskell, so it returns a string for right now. Not actually sure how it works, but it does return a string. So I think that's everything that I wanted to show as far as the global script syntax. If you have any questions, by all means let me know. If it's interesting, you want to learn more, leave comments, send feedback. I'll put a link to my Patreon in the description. If you want to see global script get done quicker, then by all means support my Patreon. And I will be back sometime soon with more videos, more syntax videos. Bye.